Okay, good morning, everyone. So today we have Hurudaya sir with us. Hurudaya sir has completed 2 years at Chennai Mathematical Institute, pursuing a dual degree in mathematics and computer science. Now at Kriya University, he continues exploring the intersections between math and computer science in fields such as group theory, logic, and game theory. Over to you, sir.
Thank you. Yeah, so pretty much like she said, I work in like mainly logic and game theory, and I felt like when Vinay sir asked me like what sessions I wanted to take, I felt like introducing you guys to like the basics of game theory would be something fun, just to like see a couple of fun puzzles that like I've interacted with, something like some of the things that originally got me into this field, and some more puzzles that like I interact with like on a more fundamental level on a daily basis. So I've just selected like 3 to 4 problems for today, and like depending on how this goes, I have a session again tomorrow, so we can like ramp up the intensity or whatever, like based on the feedback you guys give me. I want this to be like a very interactive session. Feel free to stop me at like any time just to like ask me any doubts or whatever. Like this isn't like a lecture. Like it's more like us interacting with each other, and you can like ask me questions or give me observations at any point in time. Uh, so the first thing wanted to start with is like a game that all of us have played. Rock paper scissors. One of like the main times we play rock paper scissors is if there's a tie and we want to like decide what to do, right?
Yes.
When do you guys play? Yeah, pretty much when there's a tie and we want to like decide who wins between the two of us, right?
Yes.
But why do we choose rock paper scissors as a game to play? Like why not? Like we either choose like to flip a coin or rock paper scissors or something like that. But what is it about these games that make them a good choice of game? What, according to you guys, what do you think it is?
So can I answer?
Yeah, sure. Just feel free to speak. You don't have to ask.
Yes, sir. Thank you, sir.
Hmm.
Sir, many people choose rock paper scissors or flipping a coin because it. Many people know about that game very well and they know the
Hmm.
rules, the logic behind that game. That's why rock paper scissors or flipping a coin is mostly chosen.
Yeah, perfect. That's yeah. So one thing is that yeah, it's a very well-known game. So like you can just like you don't have to explain the rules to everyone and everything. You can just do the event. Yeah, that's like an amazing answer. But then why don't we like say play a game of chess to decide who wins or something like that? Because chess is also pretty well known, right?
It's quick and it's also a game of luck. So there's and in rock
Yeah.
paper scissors there's mostly like you can find the winner very quickly.
Hmm.
In a coin toss it's just a toss to find out the winner. So it's very quick.
Yes. I want to go back to that other word you said as well. You said it's a game of luck. What exactly do you mean by that?
Like rock paper scissors may not be fully luck, but
Hmm.
it's more or less you just put something and then the other person puts something and then you just have to think what the other person would put. So it's very quick and it's just kind of lucky. Whatever it depends
Hmm.
on the other person.
Yeah.
And coin toss it's just 50-50. So it's pure luck.
So like instead of using the word luck, can I also say that like there's no strategy to the game? At least like if you're playing against a computer or something that's like randomly putting up rock paper scissors, and you're not like bringing psychology into this or whatever, where you go like people always play rock first or whatever, and like I you just have some computer that's randomly putting up rock paper or scissors, then you can't beat it, right?
Yeah.
I mean, like you can beat it, but you'll beat it exactly half the time,
Yeah.
right? So like, yeah. So like, let's say you're player one and you're playing against the computer. Okay. So you're player one, and this is the computer putting things up.
Sir, if you're writing something on the screen, we can't see it.
Okay. 1 second. You can't see me annotating? Okay.
So we can't see your screen.
Yes, sir.
Okay.
Can't see it.
Okay. 1 second. Yeah.
We can see it now, sir.
Okay. So yeah, basically what I was saying was there's basically no strategy to this game, right? It's it's a seemingly random game where if you're playing against a computer, like let's say you're player one and you're playing against the computer, right? Then what happens is actually I will replace this with your player one, and this is what the computer plays. Okay, and uh, I know Ashwin sir took like a priority session, so I'm just gonna write this, but like ask me if you have doubts. So basically, the computer has like a 1/3 probability of playing all of these because like we're playing it completely at random, right?
Yes, sir.
Yeah, and say I play rock, right? I play rock with some probability x. Okay.
Hmm.
Then what's like my expected score here? Like what percent of the time do I win and what's the probability I win and what's the probability I lose and what's the probability that it's a draw?
33.3% chance, sir.
Yeah. So like for me to win there's a 33% or basically 1/3 and for me to lose there's a 1/3 again. No matter how frequently I play X, right?
Yes, sir.
Same thing I can say for paper and scissors as well.
Sir, you
Yes.
forgot about the draw condition.
Yeah. I mean, like our probability will have to add up to one eventually. So like we'll have a draw condition. But usually when we have a draw condition in rock paper scissors, what we do is we just play the game again, right?
Yes, sir.
So like one way of visualizing it would be so like these are all my probabilities. I have a 1/3 probability of winning, 1/3 probability of losing, and then this is my draw probability, right?
Yes.
I can split this again into like a 1/3 probability of winning, a 1/3 probability of losing, and so on, right? And then the remaining smaller draw probability gets like split again, and so on and so forth, right?
Yes, sir.
So basically, what uh, you'll end up with is like there's a half chance you win and a half a chance you lose. Okay, right? Does that make sense?
Yes.
Yes.
Yes, sir.
Yeah. Okay. But here's the key thing. Okay, you have a half chance of winning and losing. This makes it a fair game, right?
Yes.
Uh, this is this is like according to me at least one of the most like intrinsic properties of both like rock paper scissors or a coin toss or whatever that makes them so popular. You have as much chance of winning as you have of losing, right? It's not like it's unfairly biased towards any one particular person.
Yes, sir.
Like say if I was going to like say instead of rock paper scissors, you guys have a running race and whoever wins like wins the bet or whatever, like whatever you guys are trying to decide on. That's not a fair game, right? Or if I say you guys play a game of chess and whoever wins the game of chess gets to basically is declared the winner. That's not fair, right? Because those are games that have strategy. Or like in the case of running, it's a game of skill, right? And strategy is just like one form of skill. What rock paper scissors provides us is a game of chance which have like an equal condition, equal win and lose condition, right? Similar to tossing a coin.
Yes.
This is what I'd like mentioned here as well. So, what's important about the game is that it's a symmetric game. What I mean by symmetric here is, if you have two players, player one and player two, right? Both of them have the same choices. So all of them can choose between um, rock, paper, and scissors, and both of them play simultaneously.
Yes, sir.
Can you explain to me why playing simultaneously is important for a symmetric game? Think of like other examples, and like tell me why.
Otherwise, like player one sees what you play and then plays, like in chess, maybe. You make
Yes. Yeah, that is one part of it, yes. But also like say for example, you're rolling a die, okay? So we have two players, player one, player two again. And first player one rolls a die, and then player two rolls a die. Player two can't really affect their outcome based on player one's outcome, right?
Yes, sir.
So would you say that that's still a symmetric game?
no.
Uh, yes, is it?
Yes,
It is a symmetric game, sir.
So that's still a symmetric game, right? So what you'll have six or 30 to 36. So basically, it'll be like like the game I just described would be like a 5/12 chance for player one to win, 1/6 chance of a draw, and 5/12 chance for player two to win again. But like yeah, what I mean is simultaneous doesn't seem like a necessary condition, but there are cases of like games where like if it doesn't happen simultaneously, even if you have the same choices, right? Uh, it might fall apart. For example, yeah, okay. So I guess I could give you this example. Um, so say you have like a game of chess or something. So if I'm just like gonna play like a quick game. So our whole thing was symmetric. So I'm basically just going to repeat the same moves that white plays for black. So if you have something like e4, black responds with e5, and then I move this pawn again and take six. Now if I take with the queen, right? Even though this seems like it's a symmetric game, black no longer has a queen here to take back, right?
Yes, sir. So it becomes
Yes,
an
sir.
asymmetric game.
Yeah. So like the fact that chess is not simultaneous means that like we're losing some intrinsic property of the game that loses it from being symmetric, right?
Yes, sir.
So if you
Yes.
want a non-simultaneous game to be symmetric, what you want is for like the two like playing boards or surfaces to be independent. Like for example, when we were rolling the two dice are completely independent. They can't affect each other, right? Like did Ashwin sir talk to you about independent events?
Not exactly.
No.
Okay. Okay, but like yeah, even like in the English sense of the word, you want them to be like two independent events that don't affect each other, right?
Yes, sir.
That's the fact that keeps tic-tac-toe a symmetric game. Sorry, not tic-tac-toe. Rock papers is a symmetric game because uh, here you need them to go simultaneously. Because obviously, if I know you're playing rock, then I'll just play scissors to win. So again, here they're like affecting each other directly, right? Compared to something like a dice roll or a coin toss. It's also a zero-sum game. What we mean by this is we don't have a condition where both um, player one and player two can win. player 1 and player 2 cannot win together, right?
Yes, sir.
Either player 1 wins, player 2 wins, or we have a draw and we go again, right? We just keep going till we get a winner, is what we're assuming. Okay. So like that's like uh oh, but here's my other question, right? If instead of this having been 1 by 3, 1 by 3, 1 by 3, I will move this. Okay. I'll just delete this for now. We'll go with different numbers. If say I give you the information that the computer has like a 1 by 2 chance of playing rock, 1 by 4 of playing paper, and 1 by 4 of playing scissors, right? And you play rock. Okay. What's your probability of winning and losing? We're talking about rock right now.
We have 1/2 probability of draw,
Yeah,
1/4 probability of losing, and 1/4 probability of winning.
perfect. 1 by 4 for win, 1 by 4 for loss, and 1 by 2 for draw. Right? Now, what if you play paper?
So the win probability if you play paper for is the win is 1/2.
1 by 2,
The draw is 1/4. The loss is 1/4.
loss is 1 by 4. Right?
Yes, sir.
And similarly for scissors?
It's
Loss is 1/2. Then win is 1/4, and then
And
draw
draw is
is
also 1 by 4. Right? So then, what would you guys play if you were playing against a computer that I told you is playing these exact ratios?
I'll most probably place paper, sir.
Why?
Sir, because it has the highest probability to win among all the three choices.
Exactly. So if you play paper, what we end up doing to that bar, if you remember, is basically this becomes win, and then there's a 1 by 4 loss, and then this is our draw. This becomes win again, and loss, and so on, right?
Yes, sir.
What this actually ends up giving us is that there's like a 2 by 3 chance of winning, right? Because
Yeah.
our probability to win is twice as much as our probability to lose. So if I just keep playing paper, then what happens is 2 out of 3 times I will end up winning, right?
Yes, sir.
So obviously there is a strategy, but there's only a strategy if the other opponent doesn't play well, right? And you need to know the information about the opponent. Otherwise, it's just random luck, right? Okay. So does everyone understand like how this comes in rock paper scissors? If you have any doubts, just let me know in the middle. Don't wait for me to ask.
Sir, can you repeat how we get 2/3 probability?
Okay, so we're just looking at this row, right?
Yes, sir.
So my win probability for that row is half, and my loss probability is 1 by 4, right?
Yes, sir.
So my win probability is double my loss probability.
Yes, sir.
So in out of the 3 cases, I'll be winning, right?
Oh, yes, sir. Yes, sir. I get it.
Like that's the intuitive way to look at it. Another way to look at it would be our probability always has to add up to 1. You guys know that, right? Like for all our possible cases.
Yes, sir.
Yeah? And we're ignoring draw because we keep going on with this same loop if it draws. That's why like there's a smaller version of it and then an even smaller version and so on. Right. But if I add these two, I'm only getting 3 by 4, right?
Yes, sir. We need 1 by 4 more. So.
Yes. Or my other option is I can just divide both of these by 3 by 4, right? Because if I divide 3 by 4 by 3 by 4, I'll get 1.
Yes, sir.
And if I divide 1 by 2 by 3 by 4, I get 2 by 3.
Yes, sir.
And if I divide 1 by 4 by 3 by 4, I get 1 by 3, right?
Yes, sir.
So this is another way of like seeing how you get the win and loss probabilities. But like the first way I explained is the more intuitive way that will help you. This is just like a formal mathematical way of getting it. But yeah. So any other questions regarding rock paper scissors?
Sir, what? What did you
Sorry.
ask?
Yeah. Do you guys have any more questions, or can I go to the next thing?
No questions.
I have a question for you guys then. I have this thing. I can clear this now. I have this thing written over here called Nash equilibrium. What does it mean? I was expecting one of you to ask me, but if you want, I will ask you guys what it means.
So it's something like rules of the game.
So Nash equilibrium basically just means uh both players have an equal chance of winning. Okay.
Okay.
So we've just named it after him because like he was the first person to find it, and it just means like no matter what strategy you have, there's always a strategy that counters it, so you both have an equal chance of winning. Okay. So I have another fun game that like we all like to play. I will come back to this. Okay. Let's look at tic-tac-toe. Okay. Yeah. Sorry. Yeah. Does everyone know how tic-tac-toe works?
Yes, sir.
Yes, sir.
So you have like
Yeah.
a 3 cross 3 grid, and taking turns, you put X's and O's, and you want 3 in a row, either on a column or in a diagonal, right?
Yes, sir. Yes, sir.
Um, have you ever noticed anything when you play tic-tac-toe? Like any observations you've noticed?
So there are a few strategies to win for sure in tic-tac-toe.
Okay. You're saying there's a strategy that you have that will win for sure.
Yes, sir.
Okay.
It's a combination of three different strategies, which
Okay.
which will always result in us winning.
Okay. What is the strategy? Like, let's play a game. You tell me where to put like an X, I'll put it for you, and then we can play.
Okay, so who's starting? You or me, sir?
Which does your strategy need?
Which player is
Or,
starting?
I mean, does your strategy need to go first, or does it work either way?
My strategy needs to go first.
Okay, then you play.
Sir, I'm putting X in the bottom left corner.
Okay. I will put a note here.
Now I put an X in the bottom right corner.
Hmm. Okay, 1 second. I haven't thought about this for a while.
You can put it in the center.
Yeah, I think going center is what I should have done. Yeah, sorry, continue.
I'm now putting an X in the top right corner.
Upright. Okay. I put a no here.
Okay, this game ends in a draw.
So you don't have a strategy to
Okay.
like. Is that there is no strategy to win every time, right? Like
Yes.
you only win if I make a mistake, right?
Yes, sir.
Why is that?
Because tic-tac-toe is already, what should I say? All different types of possibilities of games are already there. It's solved.
Right? But when we're talking about games, what do we mean by solved? What do you think I mean when I say solved?
We know when somebody loses, when somebody wins, or when it draws. Like,
Hmm.
That game has a definite solution.
Yeah, so basically, even before the game starts, based on who's player one and who's player two, I can tell you exactly what's going to happen, assuming you both play perfectly, right?
Yes, sir.
So like that's a really important condition when I say a game is solved. Because take the same example. Say you started with the same thing. I play here, like the example I played before this, and then you play here, and then I play, and then you play here. I lose this game, right? But that's because I did not play optimally, correct? Like I wasn't using the proper strategy.
Yes, sir.
Yes.
Yeah. So like we say a game is solved, assuming this perfect play. Because like even after this, right? Uh, sure, I'll just go back to this. Even after this, if he played something like this, I could have won going second as well. But
True,
like
sir.
if you're playing for a win and you're playing with like perfect knowledge of the game, you obviously won't go for that, right?
Yes, sir.
That's the important thing we mean when we say a game is solved. Is we are assuming you're playing to win, and you have all the information necessary to know how to win. Okay.
Sir, can we prove this rigorously?
Yes, I will be getting to it in a second. Okay. So yeah. So like there's like only like 20,000 possible states, right? Because like if I have a board, like there's 9 blocks, right? There's 9 of these, and each of them can have an X, an O, or they can be empty, right?
Yes, sir.
Okay. And so that means we have 3 to the power 9 possibilities. Everyone's okay with how that comes?
Yes.
Yes, sir.
Yeah? Okay. And like some of these possibilities are obviously like if I fill X everywhere, or if I fill O everywhere, or like if I put like XXX, then O, then XO, X, or something like that. Obviously, these will never happen in a real game, right?
So there should be a 5 X's or 4 X's to the game.
Yeah. So like whoever goes first, there'll be 5 of that, and there'll be 4 of the other one, right? Assuming the game doesn't end early or something like that. So
Yes.
like the total number of valid game states we have is actually 5,500-ish. Again, these are just like approximate numbers. They aren't exact. Don't quote me on them.
Sir,
But yeah,
how do we get this 9C5 or something like that?
one way to go is just like we start with our original 20,000, and then we see like how many solutions violate the condition. So like they were saying, you can see how many of them have like more than 5 X's or more than 5 O's, and then you can see how many of them have like 2 rows completed or something like that. Or like there's 1 row of X's and 1 row of O's completed, and you keep subtracting all those numbers.
Sir, but we can I think we can just choose 5 out of 9 and
Okay.
and Yeah, that's it.
So you're saying we choose 5 out of the 9 blocks,
And we
and
fill
then we put X's in them. Okay. Why that doesn't work is, say these are the 9 blocks you choose, right?
Yes, sir.
And these are the leftover blocks.
Yes, sir. Oh,
Will
yeah.
this ever happen in a real game?
No.
Yeah. Also, there can be cases of games like this, right? So I play X, O, X, O, and then X. And like I've won without completing the entire thing. So you can win even without 5, right?
Yes, sir.
Yeah. So like it's a little bit more complex than that. If you guys are interested, I'll go into it in the next session. But like for this session, we'll just like as someone else tried to ask, I'll try to prove rigorously why tic-tac-toe is a draw. Okay. So here's the first thing you'll notice. You'll see the first player, right? They only have 9 opening moves. One playing in any of the 9 boxes, right? But the more important thing is they only have 3 unique opening moves. They can either play in the corner, they can play at the edge, or they can play in the center, right?
Yes, sir.
Yes, sir.
So now for these 3 opening moves, we basically need to find optimal strategies that um, ensure that we always get a draw, right?
Yes,
So
sir.
let's start with the example he gave us originally where we start bottom left. So this is our corner condition, right? So I'll just write down. You have corner, you have edge, and you have center, right?
Yes, sir.
1 second, sorry. And you have center, right? And the counter play we found for this is we play in the center. If you play in the corner, we play in the center, right?
Yes, sir.
After we play in the center, what happens? So we have a couple of possibilities. If we'll have to see each of these possibilities one by one carefully, right? So which possibility do you guys want to see first? Okay, how about we just see the scenario he played first, where we play diametrically opposite, like diagonally opposite. Okay,
Yes.
so if you play diagonally opposite, what happens is I played here, and we decided this ends in a draw because this is forced, and then this is forced, this is forced, this is forced, and then we get this, right?
Yes, sir.
Everyone followed that?
Yes,
Yes,
sir.
sir.
So if you play diagonally opposite, I've just proved that it's forced to be a draw if you play like the right moves, like the perfect moves or the proper moves that doesn't allow for a win, right? So we don't want to play diagonally opposite. What about if you play at the other corner, one of these 2 corners?
Then the O will be forced in between the
Then
two.
the O
Yes,
and the X will
Then
be
O
forced.
will be
the
forced.
O and the X are
X will.
forced, and now I have a choice, right? I can play wherever I want, and I will choose to play. If I play here, the X gets forced,
O
the
gets
O gets forced, and then the X gets forced again.
So it's a draw again.
So it's a draw again. So we know no matter which corner you play in, it will be a draw, right? I now
Yes.
have 2 edges I need to check. I need to check for these edges and these edges, right? I'll check the close ones first because they're slightly more forced. He plays the X, I plays O.
And the
X
X,
is forced, and then O is forced,
and then X
and
is
then X is forced again, and then this is a draw, right? I can just play here, and it's a draw, right? So
yes,
near
sir.
is also forced. Okay. What about the further edge? What about this case?
Sir, O has a choice.
Okay, and what are we choosing?
So no O has 6 choices, sir. We can play
Okay.
the opposite edge. The perfect opposite edge.
If you play here, I'll play here, and then I win, right?
Sir, you have to play that spot. You have to play
Just
that spot.
play over
Like,
here,
To cancel this possibility, we have to. Yeah, that's also possible, sir.
and then X is forced here, and then
then
O
it
is forced here,
Then we have
and
3
then
choices.
yeah. Now where does X play? I mean, no matter where X plays, okay, just block it, right?
Yes, sir.
So again, so what? No matter where we play, this one ends in a draw, right?
Okay, so the closest edge.
Closer edge we just saw, right? Closer edge X plays here, then O plays here. This is all forced, and then it's a draw.
No, sir, in
Because
the option that O has a choice, the O has a choice, we told the 6 possibilities. I thought we were checking those 6 possibilities.
O does have a choice, but like if O knows that O playing in the center will make them win, why will O try to play in the edge and give X a chance? Because we just saw if O plays in the center, no matter what X plays, it's a draw, right?
Yes, sir.
So like why would O go and play something else?
No, sir, not that, sir. If we put the X above the O, above the O,
Okay.
now as we saw, we had 6 choices. In that, one
Hmm.
of those choices got cancelled out. So what about this?
You're saying play over here, right?
yes, sir.
Yes, there is still a
Uh,
chance.
yeah, but what I'm saying is, as long as we find one position for O to get a draw,
Okay.
guaranteed draw, it doesn't matter what else options O has, right? Because like all we want is for O to have a chance at drawing, right?
Okay. Oh, okay,
Like,
sir. I
hmm.
understood.
But I
So
have one small argument that X must play first 2 corners because
like this.
if X for X to win,
Hmm.
X has to have 2 corners.
Yes.
So it would be best if you can just play that in the start. So
Yeah, but even if X plays corners, we just saw that it doesn't help, right? Because it
yeah,
still ends in a draw.
but we don't have to look at the edges because if corners itself doesn't work, then edges won't work anyway.
Why?
Because anyways, first of all, X needs to conquer 2 corners to have
Hmm.
even one possibility to win.
Yeah, but
Uh,
like I can start with like the edge and then like get this corner and this corner, right? We still need to check that case.
yeah, but the best case is the case where you play the 2 corners in the start itself. Those are a bit worse cases.
What do we mean by best case here?
Like you have 2 corners already available, and you just
Hmm.
have to put an edge. So that could be like the best case.
Why
I
is
mean,
that better than having a corner and an edge and then playing the final corner?
yeah, but at some point you have to play a corner. So this
Hmm.
would be like almost the same thing. It won't make a big difference.
Yeah, but we need to check if it doesn't make a big difference, right? We can't just say it won't make a big difference. Like I get what you mean, but we need to check it still, right? Because we can't just go it's similar enough so edge will also be a draw. Because I can give you variations of tic-tac-toe where that's not the case. Like I'll try to come up with something for tomorrow, but like what's it called? Like there are situations where like we can't just directly make that statement.
Oh
Right.
yeah, wait. No, I think there's a mistake in my argument. Yeah, there's a mistake in my
Hmm.
argument.
Okay. So we still have like two cases left. So we have the case where X starts with an edge. And I think I can continue playing with a circle here again. Now what? Now how many cases does X have?
X again has 7 different cases which we all have to test.
It's 7 cases, but like under symmetry it becomes 4, right? Because like this and this are the same,
You
and this and
cannot
this
play
are
the
the same, this and this are the same.
sir, you
Yes,
cannot play sir, you cannot play the top second
Yes.
you cannot play above the you cannot play above that.
Yeah, because like it ends up, I mean, I can just play here to make it faster, but this in fact ends up
Yes,
with like O winning, right?
yes, sir, that's why we cannot play that.
So we know that's not a winning condition for X. In fact, like X instantly loses to O, so like X obviously won't play that because X also has the strategy, right? X won't make mistakes per se. X plays to maximize their chances of winning. So they
sir, I
won't
don't,
play at the top.
sir, I don't understand this case of X playing the top. That one, I don't understand it.
Okay, so if X plays on top, right?
Yes,
Then
sir.
O will play here. Okay. And
Okay.
because of this, X has to play here.
Yes, sir.
And because of this, O has to play here.
Yes,
Right.
sir.
But now O has this and this.
Oh,
And
okay.
X can only block one of the two.
Okay, sir. Understood. Thank you, sir.
Yeah. So obviously X won't play at the top middle because X also knows this will happen. So we have 3 cases left for X here, right? So
Yes,
which
sir.
let's since we started, we'll go in this order.
Okay, sir.
Next we'll see X plays here. Okay.
Now,
Now yeah.
has a choice.
Then it's the same thing as that case. So it's the
Yeah.
same case. It's a
It's
draw.
the same as playing X here and then playing X here, right?
Yes, sir.
Yes.
Exactly. So we know this one ends in a draw, right? Because I can play O here and then X O and then no matter what X plays, it will be a draw, right? Now, what about this case? X plays here.
Exactly.
I'm saying O can
The
play
row
here
will play
again.
that, sir. Yes, the row will play that, and then X will block.
Yeah. And then like no
O
matter
has
what happens, O plays here, X has to play here,
Draw.
and then it's a draw again.
draw.
Right. So now our final condition is this one.
So that's also
But
a draw.
this also we saw in this case, right?
Yes, sir.
Where like it's a completely first because O goes here, X goes here, O goes here, X has to go here, and then no matter what, it's a draw. Right. So we've just seen if X plays in the edge, it's also a draw, right?
Sir, what if O doesn't play the center, sir?
But O knows if I play, like let's say I'm second player, I'm playing O. I know that if I play in the center, I'll get a guaranteed draw, right?
Yes, sir. But what about the other cases?
So here's the thing, if I know I'll get a guaranteed draw, then why would I play something where I don't have a guaranteed draw? Does that make sense?
Oh, okay.
Okay, so now what if X plays in the center?
I want you guys to do that right now and tell me. So here's the thing. X plays in the center, right?
Yes, sir.
And
Sir, but
yeah,
now,
Sir, O plays in the edge, is corner.
but O has more possibilities, 8 possibilities to be correct.
yeah, O
Only
has
two.
8 boxes they can play in, but again
Two.
you'll notice that they're all symmetric, right?
Four.
Yes, sir.
Because like
So that's
all of the
only 2.
corners are symmetric and all of the edges are symmetric.
Sir,
So
O
there's
will
only
play
two
the
cases.
corner. O will play the corner.
Okay, O plays in the corner.
So
Then
that
what?
is so that's what it is to be draw.
So then X can play an edge.
No, now we have to check for every case for X, right? We can't just say X plays in one spot. So check for like all the cases and then come back to me.
Yes, sir.
You can't just check one case and tell me it's a draw, right?
Sir, I think I have an idea.
Hmm.
So now X plays some edge. O has to play the opposite edge.
Hmm.
And then X plays another edge. O has to play the other
Hmm.
opposite edge.
Okay.
Now any corner that X plays, X
Hmm.
wins. I mean, any corner except the opposite of the O corner, X wins.
Yeah, but that just means O hasn't played like the perfect thing. Okay, so what you're saying is X plays here, O has to play here, right?
Yeah.
And then X plays here, O has to play here. Is this what you're saying?
Yes,
Or
sir.
are you saying X plays here and O plays here?
Oh yeah, X plays that and O plays that. Yeah.
Okay, and now you're saying, but like now if X plays here, O has a thing, right? It will end up in a draw again.
Oh wait, no. I think there's a mistake. Then
Hmm.
yeah.
Yes, sir. It always ends in a draw.
It does, right?
Yes, sir.
Is
When
everyone convinced about this?
Yes, sir.
Yes, sir.
Okay. So how about this? I will leave this for you guys to try today. Just like go through all the cases yourself and convince yourself that this works. Okay?
Okay, sir.
Okay. And I will go back to this problem. Okay. Um, okay. So has anyone heard of the Monty Hall problem?
no,
Sir,
sir.
wait. I have a doubt.
Okay.
Can we generalize this to any tic-tac-toe? Like 3 by 3 is one, but then we can have 4 by 4, 5 by 5. So generalize this to any odd
Okay.
at
So
least.
generalize again is a strong word here because like it depends on what rules you're following. Say I have like a 4 by 4 tic-tac-toe, right? Are we saying that this is a win or a draw?
No,
Like,
you
are
have
we
to.
saying this counts as a win or no?
You have to get 4.
You have to get this, right?
Yeah.
Again, we'll have to go through case by case and check, but this will obviously have like a lot more cases.
Sir, I
Oh,
checked the 4 by 4 grid completely. It's always a draw. If O plays perfectly, it's always a draw.
okay. So one person is saying it's always a draw.
So
Again,
then, can we try
yeah,
generalizing it?
yeah. Try for like 4 by 4, 5 by 5 today. See how it goes. We can discuss this again tomorrow. Okay.
Yes, sir.
Yeah. Okay. So I'm just going to explain the Monty Hall problem really quickly. So you're on a game show, right? And there's three doors. There's door one, there's door two, and there's door three. Behind one of these doors is a car that you want to win. Okay, so that's the price. Behind the other two doors is a goat that you don't want to win. Okay. Uh, so there's a game show host as well, and the game show host knows behind which door the car is. Okay. And after you pick one of the doors, the game show host, like say you pick door one, right? But you haven't opened it yet. The game show host goes and opens one of the other two doors, say door two, and shows that there's a goat behind it. Now the question is, do you switch to door three or do you stay at door one? What do you do in this scenario? Or does it not matter what you do?
Sir, yes, sir, you can switch to row 3, which would give you a higher possibility.
Why does it give you a higher probability?
Because, sir, first it was a 33% chance that you are definitely that you're gonna choose the door with the car.
Okay.
Now, and a 66% chance that you're gonna choose a door with a goat.
Yes.
But after the game, then after I opened one of the doors and showed that it had a goat, the chances that you are gonna pick a car or a door or a goat have become equal.
Okay, so you're saying there's like one car and one goat. So like there's a 50% chance it's a car
Yes,
or a goat, right?
yes. And
But
sir, it's the best thing to switch from door 1 to door 3 because what should I say? I'm not sure how to explain that point, sir.
okay, here's my question. If there's a 50% chance, right, between door 1 and door 3, also I used these numbers, but yeah. If you want to switch between door 1 and door 3, right? You're saying there's a 50% chance here now. Doesn't
Yes,
that mean there's still a 50% chance here? Because we know probabilities have to add up to 1.
that's true, sir, but I'm
Hmm.
not sure how to explain it, but the probability of door 3 actually increases by like what should I say? 2% exactly. But I'll try to explain it, sir. Can you give me like 5 minutes?
Think about it. Think about it. Sure.
Thank you, sir.
What does and everyone else think we should do?
Sir, I think I kind of get what he's trying to say. He's so the let's say 3 had a goat. So picking 2 or 3 is just symmetric.
Yeah.
Or from if you think from the perspective of the game show host. So the game show host could have picked 3, but then he picked 2. So maybe that has a car, but I'm not that sure because why didn't he just pick one after he just asked?
No, so every time, no matter what you pick, the game show host will always open one of the other two doors. That's part of the game.
Oh,
We are just trying to think about whether or not switching is the right move here or staying with door 1 is the right move here.
wait, so the game show host will only pick the opposite door that you say. I mean,
No,
any
so the
other door that
game
you
show
say.
door, yeah, opens one of the other two doors. He knows what's behind every door. So he'll open a door which has a goat, and then he'll ask you, do you want to switch or do you want to stay with your original choice?
So if let's say one has the goat, then you're supposed to pick 3. I mean,
Yes.
the card, then you're supposed to pick 3.
No, you want to pick the one with the card. So you want to stay on one.
Yeah, but the game show host won't pick what you say.
No, the game show host is like opening one of the other doors to make the game more interesting.
Oh, okay. Yeah, I
That's
get
it.
it.
Like after that, if you pick one, he will open one, and then whatever is inside is what you win. If it's a goat, it's a goat. If it's a car, it's a car.
Uh, I don't think that it matters whether we switch because the probability is still half for both the doors.
So you're saying it doesn't matter if you switch or stay.
Yeah,
Okay. Any other ideas? Does everyone agree with the it doesn't matter if you switch thing then? Or
Yes,
like,
sir. Sir, I agree, but I still feel that you kept a
Yes, sir.
twist in the thing.
but you still
Sir,
feel that?
sir, I agree, but I
Hmm.
still feel that you have kept a twist in the problem.
I mean, if it was straightforward, I wouldn't be asking you, would I?
I still feel that there's a twist, even though I agree.
Hmm. Okay, I'll tell you right now, it's not a 50-50 thing. One of the two is a better option. We just want to decide which is a better option. So like I'm answering this part, it does matter. But like, should you switch doors is the part of the question I still want an answer to. Think about it. Like, try to do like actual examples where you pick a car, like imaginarily in your head, you pick one of the doors for a car. Then a person randomly chooses one of the other door. Like, write it down in a notebook, see what the probabilities are, and so on.
Sir, I think I have got the answer finally, sir.
Okay.
That switching is the best option. I can confirm it with the proof.
Okay.
Okay, so now as we know, each door
Hmm.
has 33% chance. After one door is revealed as a goat, also you have still, it doesn't change to 50-50. It still says as 33% chance,
Hmm.
but the other door becomes 66% chance that it contains a car.
Hmm. Why
Am
is that?
it's because this probability adds up to the door which you didn't pick.
Hmm.
Am I correct, sir?
Yeah, that's the right idea. So does everyone understand what he's saying?
Sir, I didn't understand.
Okay. So basically, uh, we'll forget where the car is for now. I'll just. Okay. So you had three doors to begin with, right? And you picked door one. There's a 33% chance here, right?
Yes, sir.
But there's also a 67% chance that it's in doors two or three, right?
Yes.
Yes, sir.
So the first thing to convince ourselves is no matter what we pick, because there's two doors with goats, there will always be at least one goat over here between these two.
Yes, sir.
Now what?
Like if this is a car, then both of these are goats, so we're fine. And if this is a goat, one's a car and one's a goat, so we're fine, right?
Yeah. Yes, sir.
So what we're saying is that there's a goat, assume under two or three, but there'll be one in at least one of them, right?
Understood.
What we're saying is the game show host knows that there's a goat behind two, right?
Yes, sir.
And then he opens this door. So what ends up happening is that the 67% probability all becomes part of this now. Because our original 67% was 2 or 3, and now we know it's not in 2, right? Which means it has to be in 3.
Oh, yes, sir. So 33% of the car.
Yeah, there's a 33% chance door 1 has the car, and a 67% chance door 3 has the car now.
Oh. So door
Okay.
three, you mean the 67% chance that door one does not have the car, so does not have the boat.
Yeah, exactly. Another way of thinking about this is, um, okay, how can I? What's a good
Sir, can I give
example?
another way?
Yeah, sure.
Sir, so let's say you're thinking about only sticking. So then there'll be a 33% chance because two of them would have goats and
Yeah.
they have a higher chance of being in the door. But if you switch, you would want a goat for your original choice because there'll be a higher chance of getting a car. So therefore you should switch.
Hmm. Uh,
Sir, this is an interesting problem.
yeah. Could you just like repeat your argument? Sorry, I lost you like halfway through it.
So like instead of thinking from the door's perspective, if we think from our
Okay.
perspective, we get a second like explanation. So let's say we
Hmm.
want to only stick and we will never listen to the option of switching. So that
Okay.
means there is a 33% chance
Hmm.
of winning because there are
Yeah.
two goats and one car. But
Yeah.
but if we think about switching, then we would want a goat to be in the original choice because you will have a higher chance of
Hmm.
winning the car if you switch.
Yes.
That is why we should switch.
Yeah, exactly.
Sir, but what
Now,
if the car was actually when we did not switch?
I mean, again, these aren't like guarantees, right? We're just saying there's a 33% chance if you stay and a 67 if you switch. So, like, 1 in 3 times staying will win it for you. But, like,
Okay.
the alternate explanation that he gave, I'll just explain it again for you real quick. Basically, you're picking, okay, you know what? I'll go with door 2 first, like, I want you to know it's random. There's a 33% chance this wins, right? No matter what I do to these doors, like I can open them, I can close them. No matter what, this 33% chance shouldn't change, right?
Yes, sir.
Because this was picked originally.
Yes, sir.
Yes, sir.
So until I know exactly where the car is, this 33% chance doesn't change. That's another way of looking at this problem. Because like till the game gets over, door 2 will always have a 33% chance of winning. Even if this had been like 5 doors or whatever, right? Then this has a 20% chance. And like I can open 3 of these doors and show that there's ghosts behind them. All that does is makes this a 80% chance of winning. This 20% will never change, right?
Sir,
Because
but I have a doubt.
hmm,
Now, but your choice is independent of this. It's supposed to be independent of your where the cars is, right?
yes,
So your first choice, but this doesn't seem to be independent because let's say you chose door 3,
okay.
then that means that door 1 has actually a 67% chance.
No, that means door 1 and door 2 combined have a 67% chance.
Yeah, but once door 2 is open to have a goat,
Yes,
then you again have the same thing.
yes, and then door 1 has a 67% chance. Yes.
But isn't it supposed to be independent of your choice?
Good question. It is independent of your choice, but it's not independent as a whole. Can anyone try to guess why that's the case? Like that's a really good observation. It is not independent as a whole, but it is independent of whatever door we choose. Like our original choice is an independent choice, but our final thing is not independent. Can
Sir,
anyone guess why that happens?
I don't understand what you mean by independent.
So basically, uh,
Sir, can I explain?
yeah, yeah, sure.
Sir,
What are
because
you
this
going
is
to
a,
explain? 1 second. Are you going to explain what independent is or why it's not independent?
I'm gonna explain why it is independent of the choice of our
Okay,
choice.
first, how about I just explain what an independent event is, like the intuitive idea first, and then you can explain.
Okay, sir.
Okay? So basically, his question was like originally, right? We had 3 doors, and we don't have like we're just randomly choosing one. So like there's a 1/3 probability of everything, right? And this is independent, as in it doesn't matter where the car is. That doesn't affect how we like the probability of us choosing the door, right? Because we're just choosing it randomly.
Yes.
But then, after assuming we choose one, and then the host opens door 2, right? It becomes a 33% versus 67% chance.
Yes. Sir.
Similarly, if we had chosen 3 originally, and then host opens 2, it becomes a 67% chance to 1 and a 33% chance to 3, right? And his question was, because the probabilities are changing, this doesn't seem to be independent. To me, it seems to be that it depends on where the car is,
Oh, okay.
right?
Yes.
And my question is, does anyone have an argument for why it is actually still independent? Yeah, now you can go ahead. You had an argument.
No, sir. No, sir. I made a mistake in my argument.
Okay, okay.
I didn't.
Sure. Hmm. So to whoever asked if it was independent originally, right? Here's another thing you have to consider. Uh, right. So you have three doors, right? In one, you choose this. But there's two cases. The host could close this goat door, or the host could have closed this door and kept this door open. I'm assuming you know the definition of like independent events in probability, which is why you're asking this. But like when you consider both these cases, see if the events are still independent. Does that make sense?
Uh, sir, I couldn't actually hear you the last part of what you said.
Okay, so basically every time what we've seen is just one of the cases that happens when you choose door one, which is that door two is the one that gets opened. There's also a chance it's door three that's the one that gets opened, right?
Yes, sir.
So you need to consider that case as well when you check whether these are truly independent events and how the probabilities come out to be.
Sir, but they could have chosen your door also, the door that you chose also, but they haven't chosen.
No. They don't. They can't choose door one. They don't choose the door you choose. They choose one of the other two doors and open it, and there'll be a goat behind it.
So what if we don't open door one and they choose door one?
That's another case you have to see. So like that, I'm just choosing door one every time because it's symmetrical. But like that example, you can choose door two or door three or anything like that. But like again, what happens is you're left with one chosen door with 33% probability, and then there's two doors with a combined 67 probability, right? So like in a way, those cases are symmetric, so it's fine.
Hello, sir. Just a gentle reminder. We are left
Yeah,
with the 5 minutes.
yeah,
So,
sure.
okay.
Yeah.
Sir, these doors are independent because it's
Hmm.
just a probability that the car may be inside them. It's not a 100% guarantee that the car is inside that door. So
Okay.
that is the main reason why these choices are independent.
Um,
Sir, actually, I think I have a solution for my own doubt. Yeah, I
one
just
second, one second. Let me just answer his thing. Okay, so it still remains independent even if it's a probability and not a guarantee. One example I can give you is say we're both tossing coins, right?
Yes, sir.
And your outcome, like your coin toss outcome, doesn't depend on what I get, right?
Yes, sir.
But like I can still get a head or a tail. There's no guarantee I get any one result.
Yes, sir. That's true.
Okay. Yeah, go ahead.
The
What was your
same,
solution?
so the same thing applies here.
Yes. So like
Okay,
even if it's not a guarantee, you can still have independent events.
okay, sir. Thank you, sir.
Yeah. Go ahead. What was your solution?
no, like the same solution that you proposed, but the only reason that it could even be it isn't independent is because the door that you choose cannot be chosen by the host.
You're on the right track, but also I want you to think about whether or not they're actually independent. If that makes sense, because we think they're independent, but we think they're dependent, but there's still a chance they could be independent, right?
Yes, sir. But if they are independent, then
It
uh,
has something to do with the host. It actually has to do with the fact that the host knows where everything is, so the host can manipulate the game in a way, right?
yes, sir.
So, okay, since I have like 3 minutes left, I wanted to leave you guys with like one quick puzzle. We'll go back into like a full detailed analysis of the Monty Hall problem tomorrow. I do have that lined up, but before we go, okay. So, does everyone know how like a queen moves on a chessboard?
Sir,
Yes,
sir,
sir.
I've seen this problem.
Sorry, what?
Sir, I've seen this problem.
Okay, good. So basically, what this problem is that I want to place 8 queens on this chessboard, such that no two of the queens attack each other. Okay. And what I want you guys to do is before tomorrow's class, I want you to come up with as many solutions as you can to this problem. Okay. Like, how many solutions exist is something we'll discuss tomorrow after the Monty Hall thing and the tic-tac-toe. But like, my main question for you for tomorrow is how many solutions can you find? Okay.
Yes, sir.
Is that okay? Does everyone understand the question? Do you have any doubts?
No, sir.
Sir, are there any other pieces on the chessboard?
No. You just want to place 8 queens.
Okay,
Also, just in case if someone needs clarification, a queen can attack along the diagonals it's on. So like, yeah, yeah. So like a queen can attack along all 4 diagonals, 2 diagonals, and it can attack horizontally and vertically.
Sir, your
sir,
screen
your
is not
screen is
visible.
not visible.
Oh, sorry. Yeah. So it can attack horizontally, vertically, and across all diagonals. You want to place 8 queens such that none of them attack each other. Okay? So think about both why those, like the door question is independent, why the Monty Hall problem works, and also think about how many solutions you can find for this. I know you guys have quite a few sessions, but like just try to think about any reasons you think it might work. Okay?
Okay, sir. Thank you, sir.
I think that's the end of my time, so I will let you guys take a break.
Thank you, sir.
And yeah,
Thank
thank
you,
you.
sir. Thank
Bye,
you,
sir.
sir.
Thank you, sir.
Thank you, sir.
Yes, sir.
Bye, sir.
Sir.